In this video series, we'll start talking about the representations of the Lie algebra SL2C. This video series will be very self-contained. I do not assume you know any general theory of Lie algebra or representation theory. I'll start from the scratch. First, what is SL2C? Little SL2C as a set is equal to the collection of all matrices A, B, C, negative A, where A, B, C are complex numbers. It is clear that little SL2C is a complex linear space or vector space. It's a Lie algebra because it has the Lie bracket. For matrices AB in SL2C, the Lie bracket of AB is defined to be the matrix product A times B minus B times A. With this Lie bracket, SL2C is a complex Lie algebra. So you may wonder, why do we care about little SL2C? There are tons of Lie algebras. Why do we care about this particular matrix Lie algebra? So here's the question. The reason is that you will see that general complex semi-simple Lie algebras are built out of many copies of SL2C. And it is important to understand SL2C through the finite dimensional representations. So this is a brief reason why we care about this. Now, before we start, let us recall some definitions and notations from the representation theory. So, definitions. Let V be a finite dimensional complex vector space. A complex linear representation of SL2C is a Lie algebra homomorphism. Phi from little SL2C to the endomorphism on this V. What do I mean by this? This means first, phi is a C-linear map. And phi preserves the Lie bracket. What do I mean by this? This means phi of the Lie bracket of two matrices in SL2C is equal to the Lie bracket of phi of A and phi of B. Both phi of A and phi of B are linear transformations on V. And for those two, and this Lie bracket is defined as you expected. It will be field A composed with field B minus field B composed with field A. This is an explanation for this Lie algebra homomorphism. The next notion is invariant subspace. An invariant subspace, for such a representation, phi is a complex vector subspace U of V, such that phi of x applied to U is again contained in U for any x in SL2C. The next notion is the irreducibility of a representation. We say that a representation on a non-zero space V is irreducible if the only invariant subspaces are the trivial ones, namely 0 and the whole space. So that's the definitions for a single representation. Now, given two representations, can we define their equivalence? And here we go. Two representations phi from SL2C to the endomorphisms on V, and phi prime from SL2C to the endomorphisms of V prime are equivalent if there's an isomorphism E from V to V prime such that E composed with phi of x is phi prime of x composed with E for any x in SL2C. i.e., the following diagram is commutative. The following diagram is commutative. Now you may wonder why we are using this capital E for isomorphisms. You might think maybe a more common notation for this is F. The reason that we don't use little f here is that little f will be reserved for other purposes. Now here comes the notations. This little SL2C is spanned by the following three matrices. The first one, H, is a diagonal matrix with diagonal entries 1 and -1. The second one is E, which is 0, 1, 0, 0. And the third one is F, 0, 0, 1, 0. SL2C is spanned by them three because the general matrix A, B, C, negative A can be written as a combination A times H plus B times E plus C times F. Those three matrices satisfy the following three Lie bracket relations. The Lie bracket of H and E, as you can compute from linear algebra immediately, will be 2E. And H Lie bracket F is negative 2F. And E Lie bracket F is just H. I know it is hard to memorize which is which and this Lie bracket relations, but it doesn't matter. Every time we use them, we just come back and check